here we use that that buffer geometry to kind of figure out maybe like what's deeper, where the bigger rivers are. All right, let's look at map overlays or spatial join. All right, so spatial joins are just like are typically going to be like left joins in with spatial data. So when I do map overlay, think of it as I'm doing a left join. The first one, I keep everything, but in the second data set, anything that's not in the region of the first gets kicked out. So we're going to use the MeUse data from the SP package. Going to set the coordinates. MeUse grid, do the same thing. Now let's go ahead and plot. And so we can see, here's the MeUse data set. Unfortunately, each of these variables are on different scales, so we really can't see what is going on. Now let's look at the grid. So we have some more information. Now what I want to do, an over function on this. So to explain this, I want to look at the plot that we're going to have. So here is my MeUse data sets. Okay, and okay, let me back up. All right, what's going on? I'm doing over in the SP package. Think of this as a left join. So here, this is my left data set. This is my right data set. What's going to happen is everything in here that is inside the coordinate set of this data set is going to be kept, and it's going to be appended onto this set over here. And then we're manipulating things so that things work out, and you'll notice that everything looks really much like it did in the original MeUse plots. Now, next thing we can use, or something that's also good, is for being able to do spatial aggregation. So let's say that I have data points over a region, and I want to take the average by region. And when I say region, along a grid. Right, so I've got a bunch of data points. What I want to do, I want to establish a grid where at each grid point, the proximal data points are average, summed, max, min, something like that. And, all right, so first I need my grid topology to specify where are the centers of each of the points I want to have when I'm all done. Then what I'm going to do, I'm going to take my data, I'm going to start aggregating either a maximum, minimum, median, mean, something like that. So here, this specifies where my final grid points will be. I'm establishing my spatial grid. Now let's go ahead and plot that. And so here's my grid that I'll actually have. Now what I want to do, I want to go through, I want to take the max for zinc and lead over each of the grid squares in my spatial grid. Let's see what happens. All right, so here, this is the actual grid itself. We get summary statistics, and let's plot it. And so now we can see, so the X's are where the actual data points are, and the colors represent the max for each of the squares. So I know the max of the X's of the data points in this square are much greater than the max here or the max here. So this is where this is a maximum color. So I know the maximum on the data set is here. And so this is the aggregation. So each of these squares is my grid. Each of the data points inside the square, I apply minimum, maximum, median, min, whatever it is I want, maybe sum, whatever aggregate function I want, I apply it to all the data points in this square, and that determines the color of each of these squares. All right, the next thing that we want to take a look at is normalize the difference vegetation index. All right, so what this does is takes the difference in light measured typically from a satellite with red and near red infrared, and then it's like a difference and addition and division, and that usually is used as an indication of the amount of foliage in an area. So let's go ahead and take the TM dataset that we've got, which has the light information that we need. Let's save it as a spatial pixel data frame. Then I'm going to take the part of this that corresponds to that union that I did earlier. And then let's go ahead and do principal component analysis on TM1, and this is just converting into a data frame so that it makes sense to be able to do this. I'm only taking the first 6 columns. Now I'm running the predict function to get the principal components, and then I am getting just the first 3 out of it. And now this is just to plot the first 2 principal components. And I'm choosing my color palette the way I want to. This specifies the layout and how I want my color key to appear. And so now I can see my principal components, where green is the lower values and the red, pink are the greater values for each of these. And this, remember that the over function is working to do a left join. So I'm taking this and I'm doing a left join on the region. So I'm taking the principal component values for each of the locations on the map that are included in the Olinda data sets. And here I'm doing a spatial column bind on that. And notice that we set up the row names for the O mean. So here, O mean is the left join. Set up the row names to make sure things match up the way we want to. So here, grabbing the row names here for O mean, and then I'm doing my column bind. And by setting up the row names, I know I'm going to get things to line up the right way. And so here we can see what the plot would be. It doesn't look very informative. And I can use over also to perform aggregate functions for us. For like here, for this example is median. The default is for mean, to take the average over regions as, you know, so the reason why we need this is if, let's say I have a point here on the left asset, several points near it that correspond to it. Well, how do I take these multiple points and connect to these ones? So this one data point, let's say I'll point it here, has multiple points within scale in the right data sets. In some way, some shape, some form, we need to take these and connect it to this location. All right, so what's happening is the default is to take the average. That makes perfect sense. That's that's a very good default. If I want to, I could go with median, I could go max, I could go sum, I could do any way I want to go with an aggregate function. Here we're choosing median, and we're going through and doing things very much the same way. Here I'm doing sum. And I can get these values also in my plots. And so the next few examples that are in the document are very much like repeats of just doing this with different data, with different data sets and slightly different techniques, but really morally, this is getting, I feel like it's getting redundant. So I'm going to go ahead and accelerate past it. If you want the original file, I'll give it to you. You can get it from the author's website also. We can also use Raster Stack to get information out of our data. So if I take TM1 and I use Raster Stack, we can see that it goes ahead and it gives me a pretty good looking data set. I like the default settings on this much more. I have my scales going on. Now things are smaller, so it's harder to see, but I can feel this feels like it's much easier to interpret, figure out what's going on. And we can use the extract function to extract. And so here, I've got the raster objects. I want to take the SP objects and I want to extract features to match up with the raster object. And so this is similar to that left join mentality. And this next part is just checking to see if our computations using raster match the previous techniques that we use, and we can see that they're matching up nicely. So it doesn't really matter how we approach it, which tool, we'll get the same output either way. Now, the next thing that we want to talk about is spatial sampling. So sampling, so what I've got going on is I've got my data. I might want to do some random sampling. There's, I believe, 5 different ways to do this. Of course, random sampling is the most well known. There's grid sampling, cluster sampling, stratified sampling also. And these all make sense in terms of polygons. So if over my polygon region, I can do, cluster sampling, I can do stratified sampling, I can do random sampling across all the data sets. And it's pretty much exactly what you expect. So here, the function for that in the SP package is SP sample. And then I specify my geometric objects, how many things I want to sample. Now, notice that this is going to be with replacement, and I do random. And so, all right, so this one's random. Here is a regular sampling, and of course, like once we get this, we can do, it becomes a geometric object, and I can use all the other functions for working with this like I did before. So let's go ahead and start doing some plotting just so that we can see what's going on. Here is our random sampling. Here's our grid random. And this is grid regular. And we can take a look at the empirical cumulative distribution function. This is just plotting the CDFs for us. And we can see that, there is a difference. Not much, but there is. Of course, sampling will change our outputs. And there we can get a 5-number summary going on. So the 5num function gives us a 5-number summary. So these are the numbers that are in a box plot. So minimum, first quartile, median, third quartile, and maximum. 5-number summary. Remember, a box plot is a 5-number summary. So it's just the box plot values. And boom, we can, if I run my box plot values, we can see we get pretty close to each other. All right, now there's some interesting functions that are also available in R. So these are for dealing with the sun. In map tools, we have sunrise T, and we can see that it will give us the fraction of the daylight for the day, and it will give us the time for sunrise, which is kind of neat. So if I give date time and I give coordinates, it'll tell me when is sunrise. You know, kind of interesting. We can also figure out solar noon. There's several functions for this. Solar pause. All right, well, that's all I've got for you. Take care and goodbye.